Third year in the Swagger group, and I'm currently developing a series of conductive materials for PFAS detection. And so PFAS are known as perfluoroalkyl substances, and they are commonly used in a lot of industries to make waterproof-based products for consumers, such as Teflon containers, or waterproof lip gloss, or even aqueous-forming foams to fight fires. And with that rise in industrial usage for PFAS, there has been some concern of our impact of our health, because PFAS are known as forever chemicals. They're solvated in both the fluorous phase and the aqueous phase, and so because of that, it's difficult for them to be removed from the environment, and they cause health problems. And so there has been an increase in demand for sensors to be able to detect PFAS in the water, vapor phase, and the soil. And so there's a lot of increasing in funds of $660 million to fund PFAS research and developing these sensors. And so in the aqueous phase, if we're thinking about how can we detect PFAS in our water, the EPA has a regulated pathway that's been approved, which is liquid chromatography mass spec, for analyzing PFAS in the water. But there is not an EPA approved pathway to detect PFAS in the vapor phase. So how do we know if we're breathing in PFAS in the air, and what air detectors can we use for this? That's currently a question that drives this poster presentation today. So as we can be exposed to PFAS in the air, there is a current interest in being able to detect these. And so common PFAS are PFBA, PFOA, PFOS, and PFBS, and these are the vapor pressures of these analytes, as we can see here at room temperature. And so particularly we're going to focus our story today on PFOA, perfluorooctanoic acid, and determining how we can detect this material, or this analyte, in our vapor phase. And so particularly conductive polymers are a way to quantify PFAS. So there's two ways that we can really look at detection. One, which is via colorimetric detection. Another pathway is through looking at the conductivity or the change in electrical resistivity of our materials. And so in this presentation, we're looking at conductive polymers that have this extended conjugation along the pi backbone, which allows for us to have a facile doping and de-doping of the material due to the lower band gap between the HOMO and the LUMO. And so in the case of polyanoline, this is a very stable material, and it can observe very large conductivity changes on the range of 500. And so we can see here that upon introducing an acid, we can dope our material from the emeraldine base to the emeraldine salt, and then upon treatment with a base, we can de-dope our material from the emeraldine salt to the emeraldine base. And so here is a figure of PFOA that is ultimately we take our emeraldine base, we interact our polymer with PFOA, and we can dope our polymer to the emeraldine salt. Why can we do this? Well, this acidic proton from our PFOA will ultimately protonate the backbone of our polymer and allow for us to observe, instead of an imine along the backbone, an amine. And so if we want to reduce our material, we can treat it with KOH or some type of base, and that can allow for us to transition from the emeraldine salt to the emeraldine base. And so ultimately we want to target a reversible de-doping and doping, which can allow us to continually reuse our sensors for PFAS detection. So in the past, there has been some prior art at targeting HCl vapor for PFAS detection, or for HCl vapor for PANI. And so particularly there has been these membranes that have been employed to detect HCl in the gas phase. And they employ these cellulose membranes that are coated, as you can see here, with polyanoline. And they observe, indeed, a selectivity for this acid. And so we're like, okay, how can we apply this technology to the realm of PFAS in the environment? And so in order to do that, we as chemists want to think about how we can chemically modify our polymers for an enhance in selectivity. And so particularly we're looking at tuning these perfluoroalkyl chain length and actually functionalizing aniline. So how do we do that? We take our nitro motif and we carry out an SNAR with varying perfluoroalcohols. So we have about 5 different perfluoroalkyl chain lengths that range from the trifluoromethyl all the way to the octyl substitute that's not even fluorinated. We then carry out a reduction with tin chloride, and then we can target this aniline monomer. From there, we want to target the polymer, so we carry out an oxidative polymerization with ammonium persulfate and 1 molar HCl in the aqueous phase, and we use DCM in our organic phase in order to yield the polymer. But as we know, if we have a lot of acid, the polymer is going to be in the emeraldine salt. But we need a sensor that's going to have the most selectivity. So we treat our polymer with KOH, in order to yield the emeraldine base form. So from there, we have our homopolymer. We asked ourselves, we have a lot of fluorines on this backbone, and if we want to see acid interact with this backbone of the polymer, we may want to consider a copolymer. So we have, an aromatic ring that is free and allows for increase in protonation of that polymer backbone. And so particularly we carry out a Buchwald-Hartwig cross-coupling with a nitromodi in our monomer in order to yield this nitrodimer here. And then we carry out a reduction with tin chloride in order to yield the aniline dimer. From there, we go on to carry out the same polymerization with this dimer in order to yield the copolymer here. So in addition to that, we want to understand the electrochemical properties of materials. How can we target these materials electrochemically and observe the oxidation and the reduction of our backbone? So particularly, we take out our electropolymerization, we take our working electrodes of ITO glass, we immerse it in a solution of our aniline monomers, and we continue to apply sweeps on our cycles on our polymer or on our monomer, and we observe that we get an amplification of our current as we continue to oxidize and reduce our polymer between the emeraldine base, emeraldine salts, and the emeraldine forms. And so we see here that we observe this film after the polymerization is complete. Now, in the case of the copolymer, we also observe that there is indeed, this oxidation and reduction. But in this case, we get a bulk polymerization that happens within this flask here. And I attribute that to the factorization of which this free amine is very reactive, and we're already in the dimer form. So as we add we add electrons and take away a few electrons, we're starting to actually really form polymer, and it doesn't have enough time to actually adhere to the working electrode. We've tried to functionalize the ITO glass. We've tried to change the working electrode, change the counter electrode, and we did not observe much adherence. But this is still promising for potential applications in the commercial industry where you want to bulk polymerize your materials. And these are also traces here of the films that have formed just as a blank film, so you can see what those look like as well. So from here we have our polymers that we have targeted, and we're asking ourselves, how can we apply these to sensors, and how can we use these for an impact? And so particularly we take our polymer, we solvate it in hexafluoroisopropanol, and we employ a zonial surfactant in order to yield this ink here, which is in a piezoelectric cartridge for inkjet printing. We then carry out inkjet printing onto a cellulose membrane here. And so we can see here that we do two layers. So the first layer, which is the one that's in between, is the panny inks. Then these electrodes here are copper electrodes. And we do a second layer, which is the copper electrodes, to allow for us to adhere and measure the resistance of the polymer as we introduce it to an analyte. In addition, we can consider the impact of perfluoroalkyl chain length on hydrophobicity. So we also just wanted to show here that as you fluorinate the materials, you actually observe an increase in contact angle. And if it's non-fluorinated, it has a decrease in contact angle compared to those fluorinated versions as well. So now we say, okay, we're interested in the vapor phase. So we take these electrodes here. We adhere copper wire to the two conductive copper forms with a silver epoxy, and we immerse our electrode into a vial with varying concentrations of PFOA and OA, perfluorooctanoic acid and octanoic acid, and we want to monitor this resistance over time. So we can see here that this is the printed and this is the drop casted film. So the one that says printed is the one that has been printed. The other ones are all drop casted. So I just want to show that as a comparison to see that we can get that selectivity regardless of if it's printed or not. So in the case of the PFOA, for each one of our samples, we observe a decrease in resistance. In the case of the octanoic acid, we don't observe a conductivity change at all, so it just stays consistent. And so this suggests that in the case of the PFOA, we are actually seeing an increase in conductivity or a decrease in resistance. So we're going from this emeraldine base of the polymer to an emeraldine salt, which is more conductive, and such we see a lower resistance, because those are inversely related. Excuse me. And so in conclusion, I have targeted a library of perfluorinated homopolymers and copolymers, polyanoline. I have carried out this both electrochemically and oxidatively. and been able to fabricate these materials via inkjet printing for these sensor devices that are employed for PFAS vapor. And so we look forward to continuing these sensing studies in the vapor flow and even electrochemical pathways as we harness the activity of these polymers and potentially continuing functionalizing them to have more affinity, for example, for a carboxylic acid versus a sulfonic acid group, and looking into integrating these materials into devices for portable sensing so that we can make our materials accessible for people for real-world applications. And happy to answer any questions at this time.
Oh, wow. Very impressive.
So I have a question about, like, I guess the synthesis route for like right here.
Yeah.
Like what are the yields like for like at the end of your polymerization reaction?
Yeah. So the yields for the polymerization range from about 60% to 90%. The yields are a little bit higher for our larger chain lengths, and they're a little lower for the shorter chain lengths, and that's because of the factorization of which. If you change this to a CF3 group, we know it's a good leaving group.
Yeah.
So because it's a good leaving group, there may be some types of cross-coupling that when we wash our polymer and get rid of all of the monomer, we're getting lower yields for that. But aside from that, as we go up in chain length, there's not that impact of that good leaving group of the CF3, so that allows us for us to have pretty good yields overall. We can get this nitro at the 15-gram scale, actually. And we're very serious about that. The columns were 300-gram columns. It was a fun time.
Yeah.
But yeah, so it can be scalable. Yeah.
Very good presentation. I don't know much about polymer synthesis, but how do you characterize them?
Yeah, so these polymers can be characterized two ways. So if we're thinking of the elemental structure, you can carry out SEM-EDS, which is an elemental mapping. So you can actually observe the the change in fluorine content on this test line and how that tunes. So if you want to look at elemental analysis. You can also look at different types of MALDI-TOF, which allows us to determine the molecular weight distribution, so we can see, like, at least if we get some polymer to fly. And in all cases, we do get MALDI-TOF of them, so we can see the mass-to-charge ratio and how the spacing between each mass-to-charge peak correlates with a monomer chain length size, or monomer repeat unit. In addition, we can look at the thermal properties of materials. So we've done TGA, and we've also done DSC, so differential scanning calorimetry, which looks at the glass transition and the potential melting temperature, and then thermal gravimetric analysis, which looks at degradation temperature. Those are just to consider the thermal application or ability for this polymer to integrate into a printer. So if it has a lower degradation temperature, it might degrade when you try to print it under high temperature. So those are just good things to note. You can also look at FTIR as well, look at structural analysis of the polymers. We've done solid state NMR because they're not very soluble in other deuterated solvents. And then contact angle. Yeah, that's what we've done so far.
Okay, very good. So what are some of the possible applications? I know you mentioned a few, but what else are you thinking over here?
So what I have created in the past is like filters for PFAS. So I've actually designed a filter and 3D printed this to be able to capture PFAS. And I have like an OLED screen that you can read out resistance. So that's something I want to continue on as like a future application for this, where you would design like a portable casing for this sensor, where you could see the resistance like almost like a device, and you get the OLED readout, and you can actually use it at your home ideally, or have it as something for a real world impact.
All right. Oh, wow, very impressive. Good job. So is it are you doing a PhD or a master's program?
PhD, yeah.
What year are you?
Rising fourth year.
Okay,
Yeah.
Good job, and
Thank you.
good luck.
Thank you, appreciate it.
Sure.
Thank you.
So one more time your name so that we capture it.
Yes, my name is Collette Gordon, and I'm a rising fourth year in Professor Tim Swager's group
Art.
at MIT.
Excellent.
Yes,
Thank you so much.
Thanks.